All right, welcome back everyone, and thanks for tuning in. In this video, I'm going to show how to derive the equations of motion for a double pendulum system using Lagrange's equation of motion. So as previously we saw a video on how to derive the equations of motion for a spring pendulum. This one is a double pendulum, and here's Lagrange's equation of motion, T being the kinetic energy and V being the potential energy, and q dot, the small q is the generalized coordinate. So there's two generalized coordinates here, theta 1 and theta 2. So just to show you in this figure, x1 and y1 denote the position of m1, and x2 and y2 denote the position of m2. And then the velocities of each mass are always in the tangential direction. And then these are the vectorial components of each velocity. So the kinetic energy is simply the 1/2 mv squared, and the potential energy is mass times gravity times height, using this as our datum point. So in Matlab, we'll derive these equations, we'll put them into matrix notation. So these is a second order system of equations, and then we'll use the ODE 45 function to plot and animate the results. Okay, this slide shows us the workflow. First, step by step, we're going to derive Lagrangian equations of motion in Matlab symbolically, and then we're going to prepare the set of second order ODEs, because once we derive them symbolically, we'll still have theta 1 double dot and theta 2 double dot appearing in equations 1 and 2. So what we'll need to do is do some matrix math to get theta 1 double dot and theta 2 double dot to both be on the left-hand sides of the equation. And then we're going to take that and plug it into our ODE 45 function handle. Then we'll use Matlab's ODE 45 function from a main simulation file, and then we'll animate the results. Animate and visualize the results. We'll give it some initial conditions. The system, of course, the initial conditions will be, theta 1 and theta 2, and mass 1 L1 and mass 2 L2. Okay, now we're in Matlab, and the first step is to define all of the symbols, and they're all pretty much self-explanatory: gravity, mass, lengths for the first and second pendulum. Then theta 1 is the angle that the first pendulum makes with the vertical. Theta 1 dot is the omega, or how fast theta 1 dot is changing with respect to time, and then that's theta 1 double dot is the angular acceleration. So now that we have our symbols, we can start coming up with our terms, and ultimately we want to know kinetic and potential energy. So to get kinetic energy, we need the velocity. To get velocity, we need to know how fast is it changing with respect to x and y, each pendulum. So we know that x1 is related to L1 times the sine of theta 1. That's just basic trig. And the derivative of x1, which is x1 dot, will just be the differentiating x1 with respect to theta 1. And now we need to multiply that by the inside, which is chain rule. And we can run that. Everything looks good. And now we need to know y1, which is going to be a negative L1 times the cosine of theta 1, and y1 dot equals the derivative of y1 with respect to theta 1 times theta 1 dot, because we need to use the chain rule. since theta is a function of time. Okay, x2 is the same, except we need to add the first part to it. Sine of theta 1 plus L2 times the sine of theta 2. Now this derivative we need to use the chain rule twice. So x2 dot equals the derivative of x2 once with respect to theta 1 and once with respect to theta 2. And y2 is same as before. L1 times cos theta 1 minus L2 times cos theta 2. And we just need to, we can copy paste this line. Just change from x to y. So that's y2 dot and x2 dot. So now we need to know our velocity. Let's first define some unit vectors of I and j, since we're going to be using dot product to get the kinetic energy. Throw some semicolons in there. And now v1 is going to be x1 dot times the unit vector for I plus y1 dot times the unit vector for j. And v2 will be the same, except for we'll use x2. Let's put some spaces. And y2. Okay, let's run that again. And now we need the kinetic energy. It's going to be 0.5 times m1 times the dot product of v1 with v1. Okay, so this might give us a bit of a long term. Okay, not bad. v1 equals m1 times gravity times y1 and T2 and there again. So T2 and V2 will pretty much be the same. Just change from 1 to 2. And now the total kinetic energy of the system will be T1 plus T2. And same with the total potential energy of the system. Okay, so that's it for kinetic and potential energy. Not very difficult. Now we need to take some derivatives, some partial derivatives with respect to the generalized coordinates, and then the time derivative with respect to the generalized coordinates. Okay, it's useful to check back with our equation. First thing we're going to calculate is the derivative of the kinetic energy with respect to theta 1 dot. There's a little dot there. And then the kinetic energy with respect to just theta 1, and then the potential energy with respect to also just theta 1. To find these three terms, we don't need to use any chain rule. But then when we need to use the chain rule here, because we're going to take the time derivative of this term. And theta 1 dot, and theta 2 dot, all of those depend on time, or are functions of time. Okay, we're back in Matlab, and we're going to find the terms we said we were. The first one is the partial derivative of the kinetic energy with respect to theta 1 dot. That's simply the derivative of the kinetic energy with respect to theta 1 dot. So no need to use the chain rule for the partial derivative, but the time derivative we need to use the chain rule. So the time derivative, we need to differentiate this term with respect to theta 1 dot, and theta 2 dot. Theta 1. So now we need to multiply by the derivative of the inside, which is theta 1 dot. Why is it giving me this red? Oh, okay. And now theta 1 dot times theta 1 double dot. And we need to do the same for the other generalized coordinate, which is theta 2 and theta 2 dot. So theta 2 and theta 2, and then theta 2 and theta 2. So that's the first term. The second term is going to be the kinetic energy, the partial derivative of the kinetic energy with respect to kinetic energy is T. The partial derivative of the kinetic energy with respect to just theta, not theta 1 dot, just theta 1. And we do the same for the potential energy. Okay, and then the Lagrangian equation of motion is the first term minus the second term plus the third term. So the first term is this minus this plus the third term. And now we can run that and put some semicolons here so we don't see everything. Okay, run that again. On y2, let's put a semicolon here. Run that again. So there's equation 1. It's pretty long, but what we can do is use the simplify function in Matlab. Equation 1 equals simplify equation 1. And you can see it got greatly reduced. But this is what I was mentioning earlier, that the first equation of motion has theta 1 double dot terms. Well, theta 1 double dot and theta 2 double dot. See, here's a theta 2 double dot. And here is the theta 1 double dot. So we cannot yet plug that directly into our ODE 45. After deriving equations 1 and 2 in Matlab, symbolically up here and here, we're going to write them in matrix form so we can do some matrix math to get theta 2 double dot and theta 1 double dot on the left hand side by themselves and everything else on the right hand side. So I just rewrote equation 1 here with theta 1 double dot here and theta 2 double dot here with these coefficients, and everything without theta 1 double dot or theta 2 double dot on the right hand side, and the same with the second equation. And now these two equations here, we can rewrite them in matrix form with this left hand matrix times theta 1 double dot times the column vector theta 1 double dot theta 2 double dot, simply equaling the right hand side here and here. And then to get theta 1 double dot and theta 2 double dot to solve for these, we just multiply by the inverse of this matrix. We multiply this column vector by the inverse of this 2 by 2 matrix. Okay, and now to plug into our ODE function handle for ODE 45, we declare these two column vectors, z and z dot. And z will just be theta 1, theta 2, theta 1 dot, and theta 2 dot. And if we take the derivative of z, we'll get theta 1 dot, theta 2 dot, and theta 1 double dot, and theta 2 double dot. Well, we know that theta 1 dot and theta 2 dot are simply just z of 3 and z of 4 from this. And theta 1 double dot and theta 2 double dot is what we solved for. So we're going to just plug all of that in into our ODE function handle. Okay, here in Matlab, we just basically plug in or make up this matrix M, what we showed previously. And this is the right-hand side. And then the theta double dot column vector made up of theta 1 double dot and theta 2 double dot is just the inverse of matrix M times the right hand side, and then we simplify, and then we use this subs function to replace everywhere we see a theta 1, theta 2, theta 1 dot, and theta 2 dot with z1, z2, z3, and z4. So let's run this one. Oh, we need to run it from the beginning. Okay, this is theta double dot. It's long and pretty ugly, but now we're going to use this into our and plug this into our function handle, which was done here. And I just use Notepad to replace everywhere I see a z1 with z of 1. So as you can see, here's the beginning, like that. Just copy and paste this into here. Okay, now it's time to do the main simulation. We've derived the equations symbolically here, and then we created a my function handle using the results of the symbolic equations. And I declared these as globals. You can also pass them as parameters, but I declared these as globals. M1, L1, M2, and L2 in gravity. And here's our main simulation file. We clear the screen, clear all, and clear all the figures. Declare these global parameters and define some initial conditions. I just randomly picked negative pi over 4. It's going to be at rest, the pendulum. So theta 1 dot and theta 2 dot initial is 0. Put all those into a vector here called initial values. Define a time span of 10 seconds. and then use ODE 45 and the function handle we have to solve. And we can run this one to see what those look like. So here's T and Z. Z is just a vector with 4 columns. Each column is what we defined, theta 1, theta 2, theta 1 dot, and theta 2 dot. So let's define those. Theta 1 is equal to Z, all the rows, column 1. Theta 2 is Z, all rows 2. Theta 1 dot, Z, all rows 3. And theta 2 dot equals Z, all rows 4. And change that to all rows, and then can run this again. Now we can get x and y. We can directly copy from our initial function here. X1 and y1 is just and x1 dot 2. We can get that too. Actually, we don't need it. We just need x and y. X1 and y1 and x2 and y2. X1, change this to add this notation. So that'll be a vector describing the position of the first pendulum in terms of x. So there's your x value, and now y1 is going to be the cos theta. And then x2, copy from here. And y2. Okay, and then run that. Okay, that's defines the pendulum's position x1 and y1 of the first pendulum, and x2 and y2 with respect to time as it goes through from 0 to 10 seconds. Okay, here in the final section of the code, we animate the results. We just make a for loop, and we plot a dot at location x1 here, and we plot another dot at location x2, y2, sorry, x1, y1, and x2, y2. And then we connect a line from the origin to x1, y1, and then we connect another line from x1, y1 to y2, and then we run it. Okay, GCA is get current access, and then we get a frame for each for loop, and then we run it in a movie using this movie function, get frame. Okay, let's take a look. And there's your double pendulum. Okay, I hope you enjoyed it.